On April 13, 2029, a 375-meter asteroid will pass closer to Earth than some of the satellites we use every day. It will not hit us. That is not the mystery. The mystery is what Earth might do to the asteroid as it passes. Its name is Apophis, and for one night, this ancient object will come close enough for people on Earth to watch it move across the sky with no telescope. Not as a flash, not as a shooting star, but as a steady point of light crossing the stars in real time. An asteroid the size of 3 football fields, closer than geostationary satellites, visible to the naked eye, and safe. That last word matters. Scientists have ruled out an impact for at least the next 100 years. This is not a doomsday story, but it is still one of the most important asteroid encounters ever predicted, because Apophis is not just passing Earth. Earth is going to pull on it. At closest approach, Apophis will fly roughly 32,000 kilometers above Earth's surface. The Moon is about 384,000 kilometers away. Geostationary satellites orbit at about 35,786 kilometers. Apophis will come in underneath that ring. For a few hours, a natural object hundreds of meters wide will move through a region where humanity normally places satellites. And unlike almost every asteroid encounter in history, people will be able to see it themselves. Across parts of Europe, Africa, and Western Asia, Apophis should appear as a moving point of light. Around 2 billion people will be in regions where the event may be visible. That alone would make it historic. But visibility is not why scientists care. They care because Apophis is about to become an experiment. To understand why, we have to go back to 2004. At first, it was just another near-Earth asteroid. Astronomers measured it, tracked it, and calculated its path. Then the numbers changed. The estimated chance of impact in 2029 rose to about 2.7%. That sounds small. For an asteroid this large, it was not small at all. So when the probability briefly climbed, Apophis became the most serious asteroid warning ever placed on the Torino scale, the system used to communicate impact risk. For a short time, humanity had something terrifyingly specific: a large asteroid, a measurable chance, and a date: April 13th, 2029. Then the science did what science is supposed to do. Astronomers kept tracking it. Older observations were found. New data narrowed the orbit. The uncertainty collapsed. First, the 2029 impact was ruled out. Then later, concerns faded. And after radar observations in 2021, scientists could say with confidence that Apophis will not hit Earth for at least the next century. The orbit is no longer the frightening part. The orbit is the solved part. And that is where the story becomes stranger, because knowing where Apophis will be is not the same as knowing what Apophis is. We know its path, date, distance, and that Earth's gravity will bend its orbit onto a new route around the Sun, but the asteroid is still a partially sealed box. What is it made of inside? How strong is it? Is it one solid body, or a loose collection of broken pieces? Can its surface shift? Can its spin change? Can Earth's gravity rearrange it without ever touching it? These are not science fiction questions. They are exactly the questions scientists are preparing to answer. When Apophis passes Earth in 2029, our planet's gravity will pull slightly harder on the side facing Earth than on the side facing away. That difference creates tidal stress, the same gravitational stretching that raises tides in Earth's oceans. But Apophis is not an ocean. It may not even be a solid rock. If it is strong, it may pass by and barely change. If it is weak, loose, hollow, or uneven inside, the encounter could alter its spin, disturb its surface, trigger landslides, or expose fresh material buried for ages. That is the real suspense. Not whether Apophis will hit Earth, it will not. The suspense is whether Earth will leave a mark on it. For years, this asteroid was treated as a threat to be calculated. Now, it has become something rarer, a natural laboratory flying into our reach. Earth will provide the force. The asteroid will provide the answer. And that answer matters, because somewhere in the future, another asteroid may not miss. If humanity ever needs to deflect one, we will need to know what these objects truly are, not just where they are going, but how they are built. That is why Apophis matters. Safe enough to study, close enough to change, large enough to matter, and strange enough that scientists still do not know what will happen when Earth pulls on it. The first clue came from one simple measurement. For its size, Apophis is far too light, and that means it may not be a mountain flying through space at all. It may be something weaker, something full of empty space, something waiting to be squeezed. The first sign that Apophis was not an ordinary rock was not its orbit, it was its weight. For something hundreds of meters across, Apophis appears strangely light. Its mass does not match the image most people have when they hear the word asteroid. A solid cliff torn from a mountain and thrown into space. Apophis is probably not that. Imagine two objects the same size. One is a block of stone. The other is gravel, dust, broken rock, and empty gaps loosely packed together. From far away, both may look like rocks, but if you could weigh them, the difference would be obvious. Apophis seems to belong to the second category. Its density is much lower than solid stony material. The simplest explanation is not mystery, but empty space, cracks, voids, and loose gaps between fragments. Some estimates suggest that roughly 40% of its volume could be open space. That changes everything, because a body like that is not one stone. It is a rubble pile. A rubble pile asteroid is held together mostly by its own gravity. Gravity so weak that it barely keeps the pieces from drifting apart. On Apophis, gravity may only be strong enough to keep a broken heap together. That means the asteroid may be less like a flying boulder and more like a floating landslide, a slow, silent pile of ancient fragments. We know objects like this exist because spacecraft have already met them. Japan's Hayabusa mission reached Itokawa and found a small world of boulders, gravel, dust, and little sign of a solid interior. Then NASA's OSIRIS-REx mission reached Bennu. When the spacecraft touched the surface in 2020 to collect a sample, it did not meet a firm crust. The surface gave way, and the probe sank in deeper than expected. Some asteroids are not hard worlds. They are fragile structures made of powder, stones, and empty space. Apophis appears to belong to that family. That makes the 2029 Flyby more than a close pass. If Earth's gravity pulls on a solid rock, the rock resists as one piece. But if Earth pulls on a loose rubble pile, pieces may shift, dust may move, slopes may fail, and a surface that has been quiet for ages may suddenly wake up. But density was only the first clue. The second clue came from shape. Radar observations show that Apophis is not a smooth sphere. It is stretched out and divided into two major lobes. The easiest comparison is a peanut. Another is a dumbbell. Scientifically, it may be a contact binary, two bodies that once existed separately, drifted together, touched, and stayed attached. That shape matters for one reason: the neck. Between the two lobes is a narrower region where the asteroid's halves appear to meet. If Apophis is a contact binary, that neck is the seam of the whole structure. It is where stress can concentrate, where the body may flex, settle, or rearrange if something outside starts pulling on it. And in 2029, something outside will pull on it. Earth. Not enough to destroy it, not enough to turn the sky into disaster, but enough to test it. During the close approach, Earth's gravity will not pull every part of Apophis equally. The side facing Earth will feel a slightly stronger tug than the side facing away. That difference creates tidal stress. On Earth, tidal forces lift oceans. On a rubble pile asteroid, they can shake loose material and alter the way the body rotates. For Apophis, the most sensitive place may be the neck. Think of a cracked object in your hands. You do not have to smash it to change it. Sometimes a slow pull is enough to find the weakest seam. That is the kind of experiment Earth is about to perform. And there is one more clue. Apophis does not spin cleanly. A simple solid object often rotates in a steady, predictable way. Apophis is different. It tumbles, it rolls, tips, and reorients as it moves through space, with more than one rhythm layered into its motion. That tumbling matters because rotation is not random. It carries information about how mass is arranged inside a body. If one lobe is denser, if the neck is weaker, if the inside is full of voids and uneven fragments, the motion becomes a fingerprint of hidden structure. And right now, that fingerprint is all we have. We cannot cut Apophis open. We cannot drill into it from Earth. So scientists read it indirectly, by its light, radar echo, shape, density, and strange rotation. All of those clues point in the same direction. Apophis is not a simple rock. It is probably a fragile, irregular, loosely assembled object with a weak-looking seam and a complicated spin. And in 2029, Earth will pass close enough to test all of that at once. The question is no longer whether Apophis survives. It almost certainly does. The question is what moves first: the dust, the slopes, the neck, or the asteroid's entire spin? When Earth's gravity reaches it, Apophis may answer in the only language it has: by changing. The danger of Apophis is not that it will strike Earth. The danger is that it may show us how little we truly know about objects like it. On April 13, 2029, Apophis will not simply pass through empty space near our planet. It will enter a gravitational environment strong enough to change it, not destroy it, not tear it apart, but change it in ways scientists can measure. The force behind this is familiar. It is the same force that moves oceans. Tides happen because gravity is not perfectly equal across a large object. One side feels a slightly stronger pull than the other. That difference stretches Earth's oceans into tidal bulges. Now replace the ocean with a loose asteroid. Replace water with dust, boulders, fractured stone, and empty spaces. That is the experiment waiting in 2029. As Apophis approaches Earth, our planet's gravity will pull more strongly on the near side of the asteroid than on the far side. The difference will be small, but Apophis is small too. If it is a rubble pile, its pieces may be held together by an almost unbelievably weak grip. That means even a gentle disturbance can matter. Earth will bend Apophis onto a new orbit around the Sun. But the deeper question is what happens to the asteroid itself. Its rotation is the first thing to watch. Apophis already tumbles through space instead of spinning cleanly like a planet. During the flyby, Earth's gravity will twist that tumbling body, not by touching it, not by striking it, by gravity alone. Models suggest this twist should be strong enough to measure. Apophis will probably remain a tumbler, but the rhythm may change. Its spin could become slower or faster. The direction its rotation points may shift, and the exact result depends on how mass is arranged inside Apophis. If the interior is stronger and balanced, the change may be small and predictable. If it is lopsided, hollow, or loosely packed, the response could be more complicated. That is why this flyby is not just an astronomical event. It is a stress test. For a few hours around closest approach, tiny changes in slope may matter. On Earth, a fraction of a degree means almost nothing. On an asteroid where gravity barely holds loose grains down, it can be enough to start motion. Dust can slide, pebbles can roll, boulders can settle. A slope stable for thousands of years can fail because the direction of down has changed. That is one of the most fascinating possibilities. Apophis may partly resurface itself, not globally, not in a collapse. The likely changes would be local, especially on steeper terrain. Old space-weathered material could slide away and expose fresher material underneath. For scientists, that would be priceless. In other words, Earth may scrape away part of the disguise. But the most dramatic place to watch is still the neck. If Apophis is a contact binary, the narrow waist between its two lobes is where stress matters most. Compression, tension, and twisting may concentrate there. It does not have to break for something important to happen. Even a tiny shift between the lobes would tell scientists the interior is weak and mobile. This is also the part that often gets exaggerated online. You may hear claims that Earth could rip Apophis in two, and that one piece could later fall onto a dangerous path. The idea sounds cinematic because it uses real ingredients: a weak neck, tidal stress, future encounters, and gravitational keyholes. But the conclusion goes far beyond the evidence. Apophis is expected to pass safely outside the region where Earth's tides would tear apart a gravity-held body. The best models do not predict a breakup. They predict measurable spin changes, possible surface motion, and small deformation. That is still extraordinary, but it is not an impact threat. Apophis is not expected to die. It is expected to react. And that reaction is the entire point. A strong reaction would suggest a fragile interior, looser and more uneven than expected. A weak reaction would suggest the asteroid is better locked together than its density and shape imply. That lesson reaches far beyond Apophis. One day, humanity may discover an asteroid that is not safely missing Earth. If we ever need to deflect one, we must know what kind of object we are pushing. A solid rock responds one way. A rubble pile responds another. A loose, two-lobed body may respond in a way that is harder to predict. Apophis gives us a rare lesson, a dangerous-looking object that is safe enough to study. A planetary defense experiment with no impact required, but there is one problem. To learn from it, we cannot only calculate from far away. We need instruments close enough to see the surface before the encounter, during the stress, and after the asteroid has changed. And that is why, as Apophis comes toward Earth, humanity will not only be looking up, we will be sending machines to meet it. For most of human history, close asteroid encounters happened in silence. A rock passed near Earth, gravity bent its path, and no one knew until long after it was gone. Apophis will be different. In 2029, telescopes will follow it, radar will measure it, spacecraft will chase it, and people across continents will look up and see the same moving light. The asteroid is safe, but the moment is enormous. NASA's OSIRIS-REx visited Bennu, collected a sample, and returned it to Earth in 2023. Then it kept flying. Its new name is OSIRIS-APEX, and its new target is Apophis. It will arrive after the close approach, once Earth has already pulled on the asteroid. That makes it a forensic investigator. Did the spin change? Did the surface slide? Did fresh material appear? Did the narrow neck shift? Osiris Apex will map Apophis and study how the flyby changed it. Then it will fire its thrusters near the surface, disturbing dust and stones so scientists can see what lies beneath. An asteroid's surface is like a mask. Space slowly alters the outer skin. The deeper material may be closer to the asteroid's original state. But Osiris Apex is only half of the story. Europe and Japan are preparing Ramses, designed to reach Apophis before the flyby. It can record the asteroid before Earth changes it, the before. Then, as Earth's gravity squeezes Apophis, Ramses can watch the transition, the after. That comparison is the key. Apophis becomes a natural experiment, a baseline, a stress event, and a result. The ground will be watching too. Radar and telescopes will track its shape, brightness, rotation, and any sign that fresh material has been exposed. And then there are the human witnesses. Across Europe, Africa, and Asia, people under clear skies should see Apophis without a telescope. It will not burn or trail fire. It will look like a quiet point of light moving against the stars. That may be the most powerful part. The thing will not look dangerous, but that quiet light will be a 375-meter asteroid passing closer than geostationary satellites, close enough for Earth's gravity to change its path and disturb its surface. For once, the public will not hear about a cosmic event after it happens. They will be standing under it. That is why Apophis matters beyond spectacle. Planetary defense is about understanding asteroids. A solid asteroid reacts one way. A rubble pile reacts another. Apophis gives us the next lesson without an impact. Earth will provide the force. The asteroid will provide the response. There is no hidden collision, no secret countdown. The orbit is safe. The uncertainty is not whether Apophis will hit Earth. It will not. The uncertainty is what it will reveal when Earth pulls on it. On April 13th, 2029, the world will look up and see something ancient. And somewhere in that silent crossing, Apophis will give up a secret carried for billions of years. Not by striking, but by changing.